Sodium-ion batteries are a type of rechargeable metal-ion battery that uses sodium ions as charge carriers. Sodium is accessible and abundant, making up over 2.6% of the Earth's crust. Advantages: battery-grade salts of sodium are cheap and abundant, much more so than those of lithium. These cells can be completely drained without damaging the active materials. They can be stored and shipped safely. Lithium-ion batteries must retain about 30% of charge during storage, enough that they could short-circuit and catch fire during shipment. Applications: in 2014, Aquin Energy offered a commercially available sodium-ion battery with cost kWh capacity similar to a lead-acid battery for use as a backup power source for electricity microgrids. According to the company, it was 85% efficient. Its energy density was claimed to be comparable to lithium iron phosphate battery. Performance: sodium-ion cells have been reported with a voltage of 3.6 volts, able to maintain 115 kg after 50 cycles, equating to a cathode-specific energy of approximately 400 watt-hours per kilogram. Inferior cycling performance limits the ability of non-aqueous Na-ion batteries to compete with commercial Li-ion cells. In 2015, Faradion claimed to have improved cycling in full Na-ion pouch cells using a layered oxide cathode design. SiBs store energy in chemical bonds of the anode. Charging the battery forces Na+ ions to deintercalate from the cathode and migrate towards the anode. Charge balancing electrons pass from the cathode through the external circuit containing the charger and into the anode. During discharge, the process reverses. Once a circuit is completed, electrons pass back from the anode to the cathode and the Na+ ions travel back to the cathode. Anode: Aquin originally used a carbon anode that relied mostly on pseudocapacitance to store charge, resulting in a low energy density and a tilted voltage charge slope. In many ways, titanium phosphate is similar to iron phosphate used in some other batteries, but with a low electrode potential. The initial electrolyte was an aqueous sodium sulfate solution. Later, a more soluble, less than 5 m NaClO4 was used. Using NaXC6 as the anode, the average voltage on the low potential plateau was higher for Na cells than Li cells. Unlike traditional Li cells, which make use of an intercalated graphite anode with a fully lithiated stoichiometry of Lic6, Na cells do not reversibly bind graphite. This is in part due to the larger ionic radius of the Na+ ion compared to the Li+ ion, which causes the graphite to expand. These amorphous carbon allotropes can be categorized as hard or soft. Soft carbons can be transformed into graphite through annealing at high temperatures. Hard carbon materials can be derived from feedstocks such as sugar, starch, fiber and certain polymers. Alloy anodes: metal alloy anodes made of antimony, tin, phosphorus, germanium and lead have been studied. Carbon anodes provide organic complexes for the storage of Na+ ions, while alloyed anodes form inorganic complexes with the Na+ ions, such as Na3Sb, Na3Sn and Na3P. This capability gives alloy anodes greater theoretical capacity than carbon, whereas amorphous carbon has shown capacity between 300 to 400 mAh-G-1. Na3P has a theoretical capacity of 2596 mAh-G-1. However, the alloying process requires a large volume of as much as 400%. This results in fractures and displaces the alloying material, which causes it to passivate and become dead weight, unable to accept sodium ions. Unchecked, these volume changes reduce cycle life. Much of anode alloy research focuses on mitigating volume changes and the negative effects. Cellulose: in one study, tin-coated wood anodes replaced stiff anode bases. The wood fibers proved withstood more than 400 charging cycles. After hundreds of cycles, the wood ended up wrinkled but intact. Computer models indicated that the wrinkles effectively reduced stress during charging and recharging. Na ions move via the fibrous cell walls and diffuse at the tin film surface. Another study used MOS2, graphene composite paper, as an electrode, yielding 230 Ah per kilogram with coulombic efficiency reaching approximately 99%. Cathode tests of Na2FePO4F and Li2FePO4F cathode materials indicated that a sodium iron phosphate cathode can replace a lithium iron phosphate cathode in a Li cell. The lithium-ion and sodium-ion combination would lower manufacturing costs. Triclinic Na2FeP207 was examined as rechargeable sodium-ion batteries by a glass ceramics method. The precursor glass, also made of Na2FeP207, was prepared by melt quenching Na2FeP207 and exhibited 2.9 V, 88 Ah per kilogram. Separately, chromium cathodes employed the reaction NaF plus VPO4 plus XCrPO4 NaV1 minus XCrXPO4F. The effects of CR doping on cathode performance materials was analyzed in terms of crystal structure, charge, discharge curves and cycle performance, and indicated that the CR-doped materials expressed better cycle stability. The initial reversible capacity was 83.3 Ah per kilogram and the first charge. Discharge efficiency was about 90.3%. The reversible capacity retention of the material was 91.4% after the 20th cycle.